Hello everyone. Today we are going to talk about induction and its variations. Since I don't want to make this video too long, I wrote down all the solutions already just to save time because I know you don't have enough time to watch a really long video. At the end of this document, I wrote some extra practices that you can work on. Those are just like extra stuff that you don't have to do them. Please try to do your textbook questions first. If you have more time, then work on those. The last few questions, the star questions, are a little bit challenging but still doable. But please don't freak out if you can't do them. It's normal that people can't do them in 102. So yeah, let's start. So first of all, let's talk about the principle itself. The principle of mathematical induction, PMI, is that if you have statements P1, P2, P3 till infinite sequence of mathematical statements, then if your P1 is true, and for any k in natural number P of k implies P of k plus 1, then all the statements in the sequence are true, which means Pn is true right down here. This means that which implies Pn is true for all n in natural number. Okay? Now the first question is, well, 1 square plus 3 square plus 5 square plus till 2n minus 1 square equals to 4n cubed minus n over 3. This is a really classic induction question that could be tested. So first of all, oh, by the way, this is not how I usually do induction questions, but I modified it a bit so that it matches your marking scheme for induction questions. So make sure you follow what your coordinator wants, okay? So first of all, we need to state the statement of Pn. So let's let Pn be the statement of this. So I'm a really lazy person. I didn't copy this down. I just copy paste it, which is what you should do. Just like wrote this thing again right here. This is your statement. Please do not put for all any natural number in. Okay? Now your next step is your base case. In this case, we just need one base case. So this is when n equals to 1, then you have this. Remember, for a base case, you need to show this is true. So you cannot suppose this is true and reach an equation that is not correct. You will not get marked for that. Please start with your left hand side, derived it, and eventually you actually get your right hand side. Please don't make them equal at the very beginning, okay? You need to show it is true. You need to prove it's true. Your inductive hypothesis is suppose P of k is true for some k in natural number. Again, those 2 points are really important. For some k in natural number. For some k here, please do not put for all k, because if you suppose all of the natural numbers, for all the natural numbers is true, then what's left to prove, right? So we suppose for some k is true, and we need to show that for all k it is true. The other thing is induction. If you look at the principle itself, okay, all those are natural numbers. You cannot apply induction here, natural numbers. You cannot apply induction on real numbers, okay? Please do not write for all k in real numbers. That is wrong. Please make sure you write for some k in natural number, okay? So in this case, you need to show that p of k plus 1 is true. So I wrote down the whole thing here. So this part here, wait, not this part, I mean this line here. I wrote down this line here to make my life easier, because if you look at this whole thing, it's quite complicated. So I open it up so that I know exactly what I need to show, alright? I suggest you to do it as well when you see an equation that's really complicated. Anyway, so the inductive step actually start here. So we have this whole thing, and notice that this equal to this by our hypothesis, okay? So we have this plus this, and then you just do manipulation. Eventually you should get this. I'm going like really fast because I want the video to be short enough that you don't need to spend too much time on this. But please work on the questions yourself and then come back for the video, okay? I don't want you to just like watch me doing questions, just like look at the solutions. It's not gonna be helpful. Yeah, that's about that question. The second question is another typical question for induction, when they ask you like something is divisible by another number. Again, first of all, you need to define your P of n. Just like copy down this whole thing here. Again, your base case is when n equal to 1. You'll get this, which equals to 65, which is divisible by 5. Now you suppose P of k is true for some k in natural number. Now you need to consider when n equals to k plus 1. So we have this, and you just open the bracket here, you get this, okay? Notice that here you have plus 2 minus 2. Please don't add them up. Please just don't add them up and say, oh, this is 3 to the power of 2 to the k. That's not gonna help you, because if you look at what we need to show, the original statement, it has 2m minus 2. So we need the minus 2 at the end. That's why you don't want to just add them up, get 0. In this case, we do this equals to 2 to the power of 6 times 2 to the power of 6k plus 3 to the power of 2 times 3 to the power of 2k minus 2. Well, you see that we have this. We have this, which is really similar to our hypothesis, okay? Which means you want to add those two together, okay? That is why we have, okay, this is just like calculated out. That is why we have this step, okay? This step is, notice that your 64 here can be written as 55 plus 9, okay? And then you can factor out 9, and you should get this whole thing. Alright? Now, if you look at this, our hypothesis told us this whole thing is divisible by 5, and we know that 55 is divisible by 5 as well. So if you add them together, the whole thing should be divisible by 5 as well. I don't know if Mike's gonna accept that. So I showed you the proof. So since this is divisible by 5, I wrote it as 5m for some m in integer. Then if you add them up, you can factor out 5, which shows you the whole thing is divisible by 5. I don't know what he will accept, so I suggest you to use this, okay, instead of just like argue that this is divisible by 5, this is divisible by 5. So if you add them together, it's divisible by 5. I am not sure about that, so just be safe. I suggest you to use this way, okay? Anyway, the next question is really similar to the question we just did. The reason I'm doing this question is that I want to show you that sometimes if you get stuck on induction question, you might want to use induction twice if you get stuck. I mean, it's like it's gonna take you a while to write another induction, but sometimes it works, okay? For the rest of the proof, I skipped the first parts. State P of n, the base case, the hypothesis, since they are always the same, so I didn't write them down. So for the rest of the proof, I started with the inductive step, and probably sometimes I wrote conclusion, sometimes not. But make sure when you write your assignment or your quiz, you write down everything, okay? Now, if we look at this question, we need to show this whole thing is divisible by 18. Notice that we can manipulate it, so open it up. This becomes 4 times 4 to the k plus 6k plus 6 minus 10. Again, do not add them up for now. Do not add those two up for now, okay? Because we have, well, minus 10 here, so you want to leave it there. Anyway, this we can it's like a really technique. It's a technique we use a lot of times. It's when you plus something and minus something, okay? Here, from this step to this step, I used this technique. So I want the whole thing, so I want this, and this to be together, okay? So since this has a 4 at the front, so I times 4 for those two factors as well, so we get this whole thing. And because, well, times 4, this is like 24k minus 40, but originally I only have 6k minus 10. That's why you need to minus 18k plus 36, okay? Anyway, I'm just gonna erase those. Now you can reach to your final statement that since this is divisible by 18 by IH or inductive hypothesis, we know this is divisible by 18. If you add or subtract them together, the whole thing would be divisible by 18. Again, I don't know if you can use this argument, so I suggest you use this, okay? Use this. The other way of doing this is, again, you just like open it up, you'll get this. And notice that you can write 4 as 3 plus 1 here. Well, then this will give us 3 times 4 to the k plus 4 to the k plus 6k plus 6 minus 10. So you'll eventually reach this step. And notice that you can write 4 to the k, 4 to the k as 2 to the power of 2 times k, which is 2 to the 2k. Okay, that's why we have this. We can factor out 2 and you'll get that. Well, when you reach this, you notice that this is divisible by, this whole thing is divisible by 18 by our hypothesis. But we need to show this whole thing will be divisible by 18 as well. To show that, we need to show this part is divisible by 3. Well, there is only one way. Well, for you, there is only one way to show it, is use induction again. So just apply induction on k again to show that it's divisible by 3, which works as well. But well, you can see this way is like much shorter. But sometimes when you get stuck, you need to use induction again. Go ahead, use it. It's okay. Okay. Example 4. This is another typical induction question when they give you an inequality and ask you to show the inequality holds for all unnatural number. The technique is the same. So we have to show, we need to show 5 to the k plus 1 is greater than or equal to 3 to the k plus 1 plus 2. Okay, this is what we need to show. So we start with the left hand side. We have 5 to the k plus 1. We can write it as 5 times 5 to the k. Okay, well, we have this. We know that by our hypothesis, we know this whole thing would be smaller than or equal to 3 to the k plus 2. So we use that for the next step. So we substitute this by this. We get this. Okay, now I open it up, I'll get this. Now notice that since our k is a natural number, which means this whole thing would be greater than 0. In other words, this whole thing would be greater than or equal to this. Okay, because 5 times 3 to the k would be greater than or equal to 3 times 3 to the k. Alright, make sure you understand this step. From here to here, make sure you understand it. Now our last step, you can combine those two together, will give you 3 to the k plus 1. And we know that 10 is greater than 2, okay? Which means this whole thing would be greater than or equal to this, which is what we need, okay? Can I erase those again? Anyway, this question, I have a feeling that this question is in your textbook. I'm not sure about it, but we'll still talk about it a bit because I want you to know the notation for the product and the sum, okay? Make sure you know the notation. Again, I skipped base case and hypothesis and stuff. Now it's just the inductive step. Suppose this whole thing is in the interval 0, 1. Then we have this. We need to show pi of from 1 to k plus 1, 1 minus xi is greater than or equal to 1 minus the summation from 1 to k plus 1 xi. Okay, this is what we need to show. Now, if we look at this, by definition, we should get this. Okay, So the difference is like this is like product from when I equal to 1 to k, and then you just like multiply again by the very last term. This is the last term. Alright, okay. Now you can use your hypothesis because you see this. This you know that is greater than or equal to this by your hypothesis. Notice that since we are dealing with inequality, you need to make sure that your number is positive, negative, zero. You need to be careful about that, okay? So this inequality is true because this whole thing is greater than or equal to 0. Alright, if it's smaller than 0, it's a different story. Alright, now we just open it up, you'll get this. It's like simple computation. Now you can combine those two terms together. You should get this. Okay, this is the same thing, and this whole thing should be greater than or equal to this, because this term is greater than or equal to 0. Okay, next. Okay, now we finally reached the variation of induction. The first one is when we do induction on even numbers only. I want to show you the difference between the induction on even or odd number and the induction on like natural number in general, okay? So first of all, since it's for any even number, your base case is definitely gonna change because 1 is not even, so your base case would start with 2. So when n equals to 2, we have this equals to 77, which is divisible by 11. And then you suppose your P of k is true for some even k in natural number, right? And you need to show that P of k plus 2 is true. Why is that? Because if k is even, then k plus 1 would be odd. Alright, that's why we need to show P of k plus 2 is true. The rest of the step is exactly the same as before, so I'm not gonna go through those. I might send this whole file on the Google Drive that you can just check the solution later. So I'm not gonna go over this in the video because I want to sleep right now. Anyway, we have 2 more examples. Almost done, okay? This example is another variation of induction. This is when your base case is not 1. It's not 1, it's not 2, you need to find your base case. So, we try 1 and it works. We try 2, it works. We try 3, it does not hold. Okay? Which means you cannot start with any of those because 3 does not hold. Okay? So this gives you some idea that your base case might be 4. Okay? I did not do the rest of the stuff because I think it's gonna be a good practice for you to try this question your own. I just want to mention your base case is 4 in this case. Okay? Finally, we are at strong induction. I know some of you don't get what is the difference between strong induction and induction. Here it comes. So the first then it's the same P1, P2, P3 infinite sequence of mathematical statements. This is the same. This is the same. The difference is right here. Right here. Okay? For induction, it is P of K implies P of K plus 1. For strong induction, you suppose all of those are true, okay? You suppose P1, P2 until P of K is true. And this implies P of K plus 1 is true. Then all the statements in the sequence are true. This is a principle of strong induction, okay? I saw some people only suppose P of K minus 1 and P of K are true, and then they implies that P of K plus 1 is true. Do not do this. Please do not do this. This is not strong induction. This is not regular induction. This is nothing. Okay? If you want to use strong induction, then please use strong. This whole thing, suppose all of those are true. Please do not do this. Okay? You will not get mark. Please, please, please do not do this. I know I repeated many times, but last year I repeated many times. Many students still do it. I don't want to deduct mark from you. Please don't do this. Okay. I'm just gonna erase that because I don't want you to do it. Anyway, this is a very typical strong induction question. When you have a recursive sequence, your term depends on the last term and the term before. When you see this, you know that you need to use strong induction. Why is that? Because normal induction does not give you information for pk minus 1 or pk minus 2. For normal induction, you don't know about those two. But in this case, you need information about those. That is why you need to use strong induction. Right? Another thing I need to mention is that for this type of question, usually you have two base cases, okay? And I know some people are really confusing. Some people find this really confusing. They know that they need multiple base cases, but they think their base case would be when k equals to 3, and then when n equals to 3, when n equals to 4, 5, and they ask me where do I stop? This is not right, because here when you say for all n equals to 3, this is a condition for this. Okay? This is a condition for your recursive definition. What you want to show is true for your base case is this. Okay? And we know this is true for all n in natural number. Okay, that's why you don't start with 3, you start with 1 and 2. Okay. Anyway, I'll let you do the base case and other stuff yourself. The hypothesis would be, suppose all of those are true for some k in natural number. Again, for some k in natural number. Oh my god, I'm losing all my voice. I feel like I can't talk tomorrow. Anyway, I'll try to finish this before I lose all my voices. Okay. Recursive sequence. When you see this type of question, your inductive step usually you use your recursive definition would be your first step, usually, okay, usually. And your second step would be you need to use your hypothesis. Usually, those two are the first two steps of recursive sequence inductive step. And as you can see, that's what I did here. So you need to show a for k plus 1, so ak plus 1 equals to ak plus 2 times ak minus 1. I use the definition right here. So this is by definition. My next step, I would want to use my hypothesis. So I know ak, okay, highlighter, ak equals to 3 times 2 to the k minus 1 plus 2 times minus 1 to the power of k. This is my ak by hypothesis. And I know that ak minus 1 would be this whole thing, again by hypothesis. Okay, this would be this by your IH. Okay, now you just like open it up, blah blah blah, yeah. Combine those two terms together, you get this. Those are just copy it down. Then you will get 3 times 2 to the k plus this. A lot of people, they got here already, but they don't know what to do next, because you want to show plus 2 times negative 1 to the power of k plus 1, and they see k minus 1 here and they don't know what to do anymore. Well, in this case, notice that minus 1 to the power of k minus 1 equals to minus 1 to the power of k plus 1. Okay, why is that? Because if your k minus 1 is even, then your k plus 1 will be even as well. If this is odd, this is odd as well, which means they are equal. Okay, so you can just exchange this to this, and you should get what you need to get. Alright, finally I'm done. Okay, finally. That is the end of my video. Again, I have some practice problems here. If you want to, do more questions, go ahead. I don't think I'll post a solution. I don't have time for that. So compare your answers with your buddies, your friends, your fellow students. Ask people questions on Piazza. Email me if you need to. I think everyone knows my email address already. I got a lot of emails from you guys. Anyway, good luck on your quiz. I will see some of you on Thursday.